Good morning, and welcome to session 2 of the Ampere Developer Summit. I'm Naren, and I'll be your host for the session today. Let me take a minute to introduce our esteemed guest speakers today. Vikrant Soman is a data center technologist with over 15 years of experience in product management and engineering in the semiconductor industry. In his current role at Uber, Vikrant leads strategy for server and cloud infrastructure to support Uber's multi-cloud technology platforms such as compute, storage, AI, and ML. In addition, he is actively involved in several internal and industry-wide projects that focus on making data structure infrastructure more sustainable, efficient, and reliable. Dmitry Polyakovsky is a seasoned software engineer with over 15 years of experience in building complex software. He's an expert in designing and implementing scalable, high-performance solutions that drive business success. Dmitry is the technical lead for the OCI Cache Service and is actively involved in the Valky IO project. And finally, my name is Naren Nayak. I lead a team of amazing engineers that work with customers and developers to ensure software works and works well on Ampere Silicon. In the previous session, Sean and his guests talked about the motivation for the architecture shift, the sustainability imperative, the need for hardware to be designed with the cloud-native software paradigm in mind, and a roadmap for making this once-in-a-lifetime architectural shift. What can I run on this new architecture, these new processors? What runs best? I've heard it's hard to move my applications and that I shouldn't bother. These are some of the comments and questions we've heard from developers over the years. To break through the FUD, let's spend some time talking about some workloads and companies that have made the move. Uber is, of course, the world's largest ride-sharing and delivery platform company, and Oracle's one of the largest software corporations in the world. Over the next half hour, we'll hear from Vikrant and Dmitry, who will delve into the workloads they have successfully transitioned to Ampere's processors, discuss some of the challenges they overcame along the way, and the value add that they envision from making this move. Let's do a quick recap of Pete's learning path to transitioning your applications to Ampere Silicon. Developers start by learning about the value of ARM-based Ampere processors, how a custom-designed cloud-native design is different from the 40-plus-year-old x86 architecture. What are the benefits from making some of the architectural transition? Better predictability, higher resistance to noisy neighbors in the cloud, and a design that is first and foremost energy efficient. Developers then assess their application stack, develop a phased plan to light applications up on the new architecture. The build, test, optimize, and deploy phases get into the details of the transition, and I'll let Dave and Victor expound on tips and tricks on those sections. In this section, we will focus on the learn and the assess steps. Many developers we work with are often excited about the opportunity to program towards a new instruction set. This doesn't happen very often. In our experience, a high-level playbook for choosing applications is needed, something that indicates which applications one should start off with in a structured, phased manner, rather than trying to boil the ocean, figuratively speaking. So we look at this as a Venn diagram with three vectors: effort, impact, and fit. Effort denotes the amount of work needed to migrate an application. We recommend applications that have ARM64 support today. That includes a large majority of open source applications. Impact indicates the scope of the software, and our recommendation is to focus on software that has a meaningful footprint, and so you get high ROI. And then finally, fit. If you choose applications that are a good fit for the Ampere ARM architecture, you end up with a much better outcome. Things like microservices, containers, software that has stringent SLAs that can benefit from the predictability of the architecture, and then embarrassingly parallel applications. Those are the applications we would recommend you would start off with. So let's get started. First up, we have Vikrant to discuss Uber's journey.
Thanks, Naren, and warm welcome to everyone on the call today. Glad you all could join, and hopefully, as Naren said, you will learn something about from our slides about how we went about migrating our workloads on ARM, specifically the Ampere instances on OCI. It's been a very fulfilling journey, challenging, as Naren said, in on some occasions. But I think the message, hopefully, that people can take away from this is it's possible. And I know folks here might have a lot of uncertainty about what it means to run on ARM infrastructure, and we, over the past 12 to 18 months, definitely have overcome those unknown unknowns. There are still some, but I think we see a lot of success so far with what we have seen. So let me jump into the agenda. I'll talk about why we decided to go with the ARM ISA and completely like move from x86, and why introduce this supposed challenge and complexity in our fleet. And I'll talk about motivations at Uber, which hopefully resonate with some folks on the call here. Talk about how we went about the assessment phase, or the fit phase, as Naren mentioned in his previous slide, mapping our workloads to what fits on the Ampere instance product family of products. Talk about some of the program overview, and then end with some learnings, which hopefully all of you will appreciate, and can also use it for your own internal assessment and ARM migration journey. All right, so as I said, like folks here, they are on the fence. They are like choosing whether to go with ARM. They have gotten a directive to explore ARM as an architecture to complement your x86, or they just have a new workload and they're just figuring out what's the best architecture choice for them. Where and how do you start? And over the next few slides, I hope I can share with you, I will share with you how we did it at Uber, and hopefully you can borrow some of those frameworks and decision criteria in your own assessment journey. All right. So let me recap with some of the motivations for us at Uber when we started looking at ARM architecture. And just to give some context, like Uber engineering was involved with the ARM community and Ampere community, or folks at Ampere, much before we started on the Oracle Cloud Ampere instances. So we have actively contributed to blogs and some of the open ecosystem toolchains. So you can read a blog on ZigCC, which hopefully the folks here can share. And one of the motivations that carried over even for on-prem was hardware diversification. What we saw during COVID was the supply chain risk suddenly got exposed. As our business went down, there was nobody traveling, nobody riding. We were left with a lot of standard capacity in our data centers. And we realized that we did not have too many options and did not have the right size for the capacity that we had on-prem to justify the cost that we were paying for it. And that's where we noticed that having a alternative with a different architecture gives us not only fungibility of the resource, but also fungibility of architecture that can be used for a price performance fit. And so the hardware diversification was a big deal for us. And during that time, we also had AWS, which had the Graviton roadmap, which was based on ARM. That also sort of fueled the whole ecosystem and the community to explore and contribute to making ARM-based instances a success. The other one is sustainability. That's a big deal at Uber. We have come out saying that we want to ensure that when our platform is being used by thousands and millions of active users, when they're on trips, when they're delivering food, we want to make sure our carbon footprint is minimal, or at least zero. That's the goal. That does not stop only at the rider level or the consumer level. We want to bring that back into our data centers and the infrastructure that we use to power all these applications, and millions of active users who use these applications. And that ARM, having a legacy in low power mobile processors, definitely is an interesting architecture and processor to look at, where we were looking at how to densify our racks using the Ampere processors in our on-prem. And of course, with Oracle Cloud, we are also seeing that we can get more from using the Ampere CPUs. Lastly, efficiency. Like, we want to make sure that whatever we have deployed, whatever we are using, is used optimally. And we want to make sure that your data center space, the SKUs that you deploy, they are giving us the biggest bang for the buck. And that's where like ARM complementing x86 allows us to play with this right fit. And as Naren mentioned, the assess the effort required as we migrate workloads from on-prem to cloud. This is very important for us, and Ampere has definitely given us that extra lever that we are heavily leveraging as we are on this migration journey. All right. So before I jump into sort of the effort and impact framework that Naren talked about, let me give you a quick overview of the tech stack at Uber, and how that will hopefully give you a better idea of how we went about this assessment journey. At a high level, when you order food or when you're going somewhere, it hits three distinct layers of our tech stack. And if starting from the top, you have all the application layer, which hosts all the services that fulfill your rides or fulfill your eats order. And then you have some horizontal platforms like marketplace, which make sure that you're matched with the right restaurant, your certain ETAs and prediction for pricing that is optimal for your particular journey. All those then hit our platform layer, which I would say are the execution blocks, which are app agnostic. And that includes like your payment layer, your platform, your maps platform, storage, compute, ML data, etc. Things that most of the folks here from the developer community might be more familiar with, since they are not specific to Uber here. And then lastly, all of those run on our infrastructure layer, which includes your on-prem data centers, you have your cloud zones, your switches, your network and cabling, all the physical layer that hosts the platform and the application services. So in terms of numbers, like all this, those three layers are designed to serve tens of millions of trips and predictions every second. And what that does, it generates like terabytes of data in real time that is flowing through all of these layers in aggregate. Which is why like having something like Ampere instances is very important for us, because it allows us to create a chance for reliability and availability with such a diverse technology footprint, and allows us to maintain availability across all our product portfolios and applications. So how do we go about like selecting which ones to start with? Going back to the effort, impact, and fit, we did a lot of that with Naren's team as well as other folks at Ampere, Oracle Cloud, figuring out where do we start, what what is our low hanging fruit, and if not, like what's the ROI if we need to put in some effort. And we decided to finalize on our compute stack, which hosts thousands and thousands of microservices that are written primarily in Go and Java. And Naren can tell you, like Java as an ecosystem has come a long way. Even when I was in my previous organizations, like getting Java supported on ARM was a big win. And now we have come a long way, and we are seeing some of the success of that as we started exploring which workloads to migrate onto Ampere instances. As far as the other one we looked at was storage, streaming, and search. And those are some of the popular database technologies, which are, and I'm going to use that phrase that Naren said, embarrassingly parallel. If you think about MySQL, where you can scale out the threads, get some of the throughput that you need without exercising too much of compute capacity, because databases are, as you folks know, are storage bound. So we looked at Cassandra, Redis, MySQL, Kafka, and of course we have other in-house database technologies, which I did not call out here. But in terms of like the footprint, these are massive. Like even though there are two or four words here that I've highlighted, in terms of the impact, it's massive for us in terms the ROI that we saw. So again, we looked at other inputs, strategic roadmap from Oracle Cloud, Ampere, etc., which I won't go into details here. So how does that look? And if I had to plot it in, is this at a high level in terms of impact and effort? Of course, we started with some synthetic workloads using spec, which is not really a workload we use anywhere, or not. I'm sure developers don't deploy that in production, but low effort, low impact in the sense that the benchmark exists. We were able to run it out of the box, get a baseline of what to expect for the Ampere instances. And then we started looking at, if I go from the top, Golang is the one where we are spending and did spend significant amount of time, not only like debugging issues, but also like figuring out what benchmark to run. What does Go performance really mean when you are migrating your services? So optimizing Go runtime configurations is, I would say, we spent quite some effort on that. Compute on the Java side, again, it was more in-house. The effort was on migrating from JDK 11 to 17, not so much from an ecosystem, which is really robust at this point. And storage, again, very low effort. Redis, Cassandra, binaries just built out of the box. We ran the workloads. Of course, there's some time spent in enabling the dependent libraries, like async profile of a Cassandra comes to mind. But again, some workloads ran out of the box. Some needed a bit more effort, but I just put a quote here, like workloads eventually shine. Like it's not like nothing works, which a lot of folks here might be like, oh, does it work on ARM? Is a very uh, uh, appropriate question to ask for someone who has never tested or ran workloads on ARM. So hopefully this lays that to rest. Workloads run, they also work really well. All right, so summarize with some learnings. I know probably a minute over, but just wanted to highlight this. A lot of folks who start on their assessment and learning journey assume that low power means low performance. And what we are seeing over and over again is Ampere CPUs have enough horsepower to give you at or better throughput than the incumbent AMD or Intel. So don't take benchmark the values at face value. Run your own workloads, see what happens, do your TCO analysis. There is also the benefit of linear scaling. If you are thinking of packing more and using the CPU at high utilization, you'll be surprised at the impact of having SMT versus not having SMT. That's certainly starts showing at above 50%. Benchmarking cluster applications and example of Redis or Cassandra for us requires some extra care and attention. Like when we ran the benchmark out of the box, the performance of Ampere came a little shy of what we saw with other offerings. But that was not because of the Ampere CPU itself. It was how the host was placed. Where was your Redis mem tier client relative to the cluster, the zone topology, the networking? That was actually what was causing the issue, and not so much the CPU architecture or the CPU product. So things that we learned along the way and how we had maybe looked over some of the benchmarking philosophies in our past life with having only x86 architecture. So it helped us fortify our benchmarking frameworks as well. Working with Naren's team of and his amazing engineers, lots of optimization techniques that we learned, and as engineers and developers, that is certainly a fulfilling thing. Like when you learn something, that's important. We learned how you can optimize your performance and not like just say that okay, this is the best we can get. No, you need to ask the question, what else can we do? And there was a mindset shift at Uber and how engineers looked at instances and hardware performance and application performance. This hardware software co-design really came into picture, and that has helped us really push the boundary of ARM performance or Ampere instance performance as we are migrating our workloads on the instances. All right, with that, I'll hand it back to Naren.
Thank you, Vikrant, for sharing your lessons and expertise for other developers to benefit from. I know it's been a monumental journey for you guys, and between Oracle, Uber, and Ampere, I think we've learned a lot. Next, let's hear from Dmitry and the journey the OCI Cache team at Oracle has been on.
Hello, my name is Dmitry Polyakovsky, and I'm excited to be presenting here to you. Let's first start about what is Oracle Cloud Caching Service. We basically offer a managed Redis service. We launched last year, and we offer Redis 7. And behind the scenes, we use the Oracle Cloud technology called Flex Shapes. It allows us to specify exactly the amount of RAM you need. So if you need 7 gigs of RAM for your cache, no problem. And if tomorrow you need to go to 27, you can easily resize your Redis cluster with no downtime in a matter of minutes. And behind the scenes, to provide this service, we utilize both ARM, Ampere, and AMD processors. Redis on ARM has been supported since 2017. And the challenge with Redis is it's written in C. So we had to do some extra work to make sure it compiled for ARM on Oracle Cloud Linux. Redis is mostly single-threaded, and I'll talk about why that's important. Well, let's ask the most obvious question. Why did we need to choose Ampere to run Oracle Cloud Caching Service? The biggest challenge was capacity. When you're running a cloud operation, you're essentially running a large hotel. And at any moment, customers can show up, and you have to provide them with capacity. And it's especially can be challenging when they're asking for very large clusters. So if you want, let's say, 5 gigs of RAM for your caching solution, that is usually very easy to find because we have a large fleet of computers and they have a little bit of memory here or there. But if you want to have, let's say, 500 gigabytes of RAM for your cache, well, that entire 500 gig has to be on a single physical server. And that can be harder to find. So by using both Ampere and AMD chips, we're able to diversify our capacity infrastructure, and we increase our ability to provide you the Redis clusters that you need. Another important issue is energy efficiency. Again, these are very large data centers. They require a lot of electricity, and Ampere is more energy efficient. So we're able to not only save money and reduce our environmental footprint, but also literally sometimes just we need that extra power. And last, and obviously not least, it's the price performance. We're able to utilize Ampere to decrease our overall costs, and we increase our ability to provide you the Redis clusters that you need. Another important issue is energy efficiency. Again, these are very large data centers. They require a lot of electricity, and Ampere is more energy efficient. So we're able to not only save money and reduce our environmental footprint, but also literally sometimes just we need that extra power. And last, and obviously not least, it's the price performance. We're able to utilize Ampere to decrease our overall costs, and we can pass those savings on to our customers. So how do we use Ampere? Well, as I mentioned, Redis is C. Redis is written in C, and it works on both AMD, x86, and Ampere ARM architectures, but we have to compile it appropriately. So we have to design a build process that compiles Redis for ARM and for AMD. And then we basically create virtual machine images with Redis pre-installed, and also we put additional configuration files and certain startup scripts needed. And we distribute these images to both of them, to every one of our data centers. Now then, we use something called Oracle Cloud Instance Configuration. And what instance configuration allows you to do is to choose the right shape. And this is a public Oracle Cloud technology, and anybody can use it. So here is a screenshot of one of our systems where we have 4 different configuration options defined. And when you call Oracle Cloud Compute APIs, you simply specify this instance configuration, and Oracle Cloud will give you a computer that meets one of these options. And that's something we actually had to learn along the way, because at first we actually had a much tighter relationship. We kind of, you can say, hard-coded in our code what are the shapes we're using. But later, when we introduced this instance configuration abstraction, it made our code much easier. We are now able to add or remove different shapes as we need to, and it can be configurable on per data center if necessary, and we can leave our code much more simple. So what are some of the lessons learned? Well, we learned that it's really important to test very, very carefully. And even though it's the same Redis code in C, and it works for both Ampere and AMD, in reality, you're going to have certain operating systems configuration changes that are custom to that particular chip architecture. And you also may have certain startup scripts that also may work a little bit differently. So we invested a lot in automating of testing of the Redis servers on both Ampere and AMD, and also not just functionality testing, but also performance testing, which I'll talk about in the next slide. Another thing we learned about is that you really want more than one CPU, because when you run Redis and operating system and various background agents you inevitably have on one CPU, your performance is just abysmal. And we also learned that we need to provision extra RAM for the operating system and those background processes. When you provision a Redis cluster with 10 gigs of RAM on Oracle Cloud, you get 10 gigs of RAM guaranteed for Redis, and anything needed for the OS and other overhead is we provide it on top of it. So let's talk about performance. When it comes to performance, it's very important to differentiate localhost performance versus network, realistic, real-world performance. And this is where I'm really agree with what the Uber engineers discovered, that it's not just chip, it's all kinds of other variables involved in the overall performance of your system. So when we were running localhost tests, that yes, Ampere was not as fast as AMD, that is true. However, customers don't run Redis locally when they use our service. They run their applications on their service in their network, and we run Redis for them in our network. So they access Redis remotely. And when you take that into equation, there in the real network world, the performance difference is quite negligible. And when it comes to price performance, that obviously puts Ampere ahead. So to run these tests, we use these 2 tools, Redis Benchmark and Ampere Benchmark. You can download them from GitHub and try it out for yourself if you need to. But again, I'm going to second what Uber engineers talked about, is that benchmarks are very useful, but you really need to run your workloads in as realistic as possible scenarios as you can. So, I want to briefly touch on Valky. Valky is a recent fork of Redis, and what Valky 8, which was literally introduced just last week, introduces is multi-threading. So we at Oracle are very interested in trying it out, and we'll be offering Valky as a managed service in the near future. And we want to take advantage of additional cores using Valky 8 multi-threading. And we will be able then provide just higher throughput on a single server by utilizing those additional cores. Well, that's it. I hope you enjoyed my presentation. Are there any questions?
We've got lots of questions, but first, thank you,
Okay.
Dmitry, for sharing some of the challenges of deploying an as-a-service product in a multi-architecture environment. Like Dmitry said, let's move on to Q&A. I'm going to pick a few questions for both Vikrant and Dmitry from our Q&A. So this one's for Vikrant. Vikrant, you mentioned, Uber has started their ARM journey years ago, and I know personally you have experience from your past lives working with the ARM architecture. In general, what have your observations been around software support for ARM and Ampere from a functionality and performance perspective?
Great question, and that's gives me a chance to also sort of like look back and reflect of 10 years worth of being exposed to ARM architecture and ARM products, and starting way back when, I think I was telling you the other day, getting Linux to boot on ARM was like a big deal, and I remember celebrating that day when we were running that on our products, ARM products. So from that point to, like, as I mentioned today on, like, I was talking Redis, Cassandra, Java, just running out of the box. That's just a testament of all the ecosystem contributions that have gone in making ARM, ISA, and the ARM architecture a first-class citizen within the developer community. In terms of support, like, I can give you like the generic out-of-box experience with Linux kernels. Like, of course, things boot, and you don't have to like tweak anything. You don't have to like modify any settings. Specifically for your team and folks at Ampere, I think I mentioned that in the learnings, the optimizations and the know-how of the architecture, that has, at some point, it is less about the ARM. Like, you folks know ARM ISA very well. The implementation of the ARM ISA as a chip, and then that translating that into what it means to run your software efficiently. I think that's where really your team and Ampere has done an amazing job of providing those knobs and sort of that translation for developers who might not know, oh, this is how the chip runs. This is what instructions are supported by the ARM ISA. Hence, my software needs to be written in a certain way. That, I think, a lot of folks say that, oh, we wrote software in XYZ way, and they expect it to run out of the box. That, I think, as I said, I mentioned hardware, software, co-design philosophy. I think that has something that your team and folks at Ampere have really done a phenomenal job with all your white papers, runbooks, working with customers such as ours. So yeah, the support is there. Ecosystem support has always been there. I talk to folks at ARM very, very frequently. And I can see, like, as soon as I mention, oh, this is a project that is there support for ARM? Like, of course, yeah, we have this particular GitHub link that you can go, and we're already working with folks at even Intel, AMD. So it's no longer this like where ARM is operating in a vacuum and the ecosystem is sort of like a step function behind. No, it's right shoulder to shoulder with how the x86 ISA works. So that's, I can go on and on, but I think I'll pause.
All right, thank you. Yeah, and I know this is easier said than done, but we like to tell developers just use the latest stuff. Right? The ARM ecosystem has made tremendous progress over the last few years from a stability point of view, performance point of view. Newer versions of software will give you tremendous improvements in performance.
Yeah, I would
all
like
right.
to maybe clarify that point. Like, yes, it's going to latest is good, but I think mentioning the reasons of why that is important, what changes made, I think it really helps sort of tie in that answer properly, and you folks like give us that clarity, which is very helpful for developers to say, oh, it's worth doing it, and this is why it's important. So
awesome, thank you for the compliments. This one's for Dmitry. I know one of the more compelling class of applications to make an architectural transition is as a service offerings, because the choices you make on the back end are hidden from the developer or the customer. As long as their SLAs are met, they really don't need to know what architecture, what operating system your product's running on. Do you have any tidbits from your journey to your current multi-architecture Redis deployment?
It's a good question. Yeah, so we actually started originally on AMD when the project was originally launched a few years ago. Well, when the project was started, not when we launched. But we jumped on the ARM bandwagon about 2 years ago when OCI became heavily invested in it. And well, our challenges were particular to the fact that a lot of the internal tooling at OCI wasn't yet quite supporting ARM. So we had to, improvise a few creative workarounds. But since then, Oracle overall has, in fact, you could say my team was a pioneer of prototyping ARM for data plane to run, Redis or other databases. So yeah, I guess that was our challenge. We were just on the cutting edge internally at Oracle.
Got it. And then thanks, Dmitry. And a follow-up question. There's a couple of questions around Valkey. Was the Redis license change the primary motivator for migrating to Valkey?
Okay, so I can speak about the Valkey project in general. Yes, so the Redis community has just decided that it would make sense to move to fork the project, and it's a difficult decision because Redis is a very popular technology, but changing the license meant that you were no longer free to innovate as much as possible. So that is why the fork occurred a few months ago. And yeah, I would say that the speed of development and innovation on Valkey has been much greater. It's an open project under the umbrella of Linux Foundation. And it has people involved, myself from Oracle, there are engineers from AWS, from Google Cloud, from Alibaba, who are actively contributing to the code. So yes, license was the forcing function, but I think the speed of innovation on Valkey has picked up quite significantly. And again, just want to say that one of the priorities for Valkey project is to maintain backwards compatibility to Redis as much as possible. So like right now, if you are interested in migrating, you can literally launch Redis, launch Valkey server, make it a replica of Redis, replicate your data, and switch over. The APIs are 100% compatible at this point.
Fantastic. Thank you, Dmitry. It looks like that's all the time we have. This has been a very interesting discussion. Thank you, Dmitry. Thank you, Vikrant, for your time. It's been very interesting listening about your experiences migrating to Ampere's processors. Next up, just a reminder, we've got Victor talking about deploying AI in production in a cost-efficient manner. So please make sure to tune in, and thank you.